I'm going to circle back to the swimmer problem we did a couple of videos ago. If you didn't tune into that video, you can still follow along with this. I'll give you enough information. But what we did in that video is we had a swimmer, and that swimmer had a swimmer speed. She could go 120 feet per minute. And the river, the water, had a current of 25 feet per minute. And when we did the last problem, we looked at the fact that the swimmer can swim across. The river width was 1,000 feet, so we'll keep that. So if the river wasn't moving, the swimmer could swim straight across and land here at 120 feet per minute. But if the river has a current, we realize that as the swimmer tries to go across, the current pushes the swimmer down, and she landed way down the river somewhere. A couple hundred feet it was. Well, what if she has to land straight across? What if there's some kind of rapids, or there's a dam, or something, and she's brave enough to try to swim across, or foolish enough, right? We don't want to do something dangerous. But how does she get over directly across from where she started? Well, I think you all have the intuitive knowledge from just being outside and dealing with things that she has to swim upstream. So she's going to have to swim upstream, and then the current is going to pull her downstream. And if we orient our problem that way, then her resultant velocity would be straight across the river. So my question is, given this information, at what angle must she head to land directly across? And then, how long will it take her? We found in our last video it took 8.33 minutes for her to go across if she headed straight across and let the current take her down and she didn't land straight across. Okay, so what angle must she head off at? Well, we know this is her velocity. That's the 120 feet per minute. This is the current velocity. This is 25 feet per minute. And so the triangle gets set up pretty quickly because we're looking for at what angle must she head. So instead of heading straight across, we want that angle. And we have a very clear triangle right there. So we can just say that the angle, we can use the sine of the angle because we know the opposite side is 25 feet per minute and the hypotenuse is 120. So the sine of that angle is 25 over 120. So the angle will be the sine inverse of 25 over 120. And when you do that, you get a 12-degree angle. So she has to head 12 degrees upstream, okay, or 12 degrees in standard position if you want to look at standard position. So that's the answer to part A. Now part B, how long does it take her to cross the river? Well, when she lands here, this part of her, that resultant vector, that's going to be the velocity that gets her across the 1,000 feet. So we know that the distance she swims is equal to the velocity times the time, and the distance is 1,000 when her velocity is this resultant velocity. So we'll call that V across, VA, times the time. And if we want to find how long it takes for her to go across the river, then we need the magnitude of that resultant vector, which we can get because if we look at this triangle, we can either add these two vectors, or you can see that this has made a right triangle, so we can use our Pythagorean theorem and say, well, the velocity across squared plus 25 squared, that's going to equal 120 squared. And the reason that this works is because the across and the downstream, these are perpendicular to each other. So it doesn't always come out this way, but on crossing a river, the across and the downstream are perpendicular. And so the V across is going to equal 120 squared minus 25 squared, and then square root both sides. So we get that the velocity taking her directly across the river is going to equal square root of 120 squared minus 25 squared. And so her across the river velocity is 117 feet per minute. And so we can calculate the time because we know that the time will equal 1,000 divided by the velocity that's taking her across. So 1,000 divided by 117. And we get the time for her to cross the river and land safely on the other side is 8.5 seconds. And that's how you can use vector addition with across and downstream and take advantage of your right triangle situation. Now we could also have done this in more of a traditional vector addition problem, and we could have looked at the triangle if I just draw it, just so that you see the two different ways. So we have the 120 and the 25, and this is our resultant vector because we're adding now, right? So we have v of the swimmer plus v of the water, and that's going to equal our resultant. And so our resultant vector is equal to the sum of the velocity of the swimmer plus the velocity of the water. And if we put these in component form, we know that the velocity of the water is going to be 0 minus 25 because I'm calling across to be x and the y-axis is the river direction. And so I'd have to find out the components of this across the river vector. So I would put an angle in here. And I would say that across the river vector has a component of 120 times the cosine of the angle she heads and 120 times the sine of the angle she heads. Right? So those are the components of this vector. 120 cosine and 120 sine of the angle. That's her resultant. Now, if I want my resultant vector to be directly across the river, that means that I want an x piece, but I don't want any y direction. I don't want her to be going up or down the river. So that means that 120 sine of the angle plus negative 25 has to equal 0 in order for the across vector to have 0 in the downstream direction. When we add these two, and I like to show them adding like sort of stacked up, so I'm going to do it this way, 120 cosine of the angle and 120 sine of the angle. And if I add that to 0, negative 25, to get my across the river vector, right, I want these two to add up to 0 because that allows me to go across the river. And so really, looking at it in terms of this vector perspective, when I add these two up, I get 120 sine of the angle equals negative 25. And so I get the sine of the angle is going to equal negative 25 over 120. And so when I do sine inverse of that, I'm going to get that the angle has to be negative 12 degrees, and that would be the angle going this way. And so if this angle is,